doesn't work. Okay, so now we are being recorded. So before we get started talking about physics, does anybody have any questions? Any quick questions before we get started? I will get our PowerPoint going. Okay, I don't see any questions. So, okay, someone says they need help from number 12 on the homework. So I would say that to please come to office hours this afternoon. Or there was a hint in the discussion board. Somebody else was asking about number 12. So maybe go look at the Canvas discussion board. That might help. Or if you want, you can ask a quick question at the end of class today. So as you probably know, one of the topics we're going to talk about today is circular motion, and that's why I chose this particular Calvin and Hobbes comic for today. And the reason I like this one is because in some ways, uniform circular motion seems simple, but then if you think about it, sometimes it's a little more complicated in some respects than it might seem at first. So we're going to talk about that today. Just a few announcements before we start talking physics. So one heads up is that I had to change my office hour today. Normally my office hour today would be from 1 to 2 p.m. But just for today, I've switched it to 3 to 4 p.m. And that's because I had a meeting that got scheduled before I had a chance to tell these people I had an office hour at that time. So I have to switch just for today. A reminder to remember to purchase access to Achieve soon. Sometimes people have a little trouble doing the switch over from the free access to the paid access. So the sooner you do it, the better. In case there are any hiccups in the transfer over, you'll have time to sort it out before you lose the free access. A lot of people are going to lose the free access next Monday. Remember that if you're planning to take Physics 121 in the next few semesters, to purchase the 2-term access, it'll save you a lot of money. Okay, because the 2-term access is only a little bit more than the 1-term access. Remember that we're going to start using iClicker next Monday, so set up your account soon if you haven't already. And then one more thing is that we're going to have our first written homework assignment. Will be posted in Canvas today. It's going to be posted as a quiz where you will enter a numerical answer in Canvas, and then you will submit your work that you did to get the numerical answer into CrowdMark. And so I've set the CrowdMark up. And so after class sometime today, you will get a CrowdMark announcement about the assignment, and I will make it visible on Canvas. And I tried to explain how it all works in both Canvas and CrowdMark. So, but if you still have questions, feel free to ask them in the discussion. And this will be due next Monday. It's due Monday, January 24th. So we will have a written assignment maybe every other week, and I think they'll typically be due on Mondays unless something else is going on and I shift it to a different day. Any other questions about that? Okay, good. I don't see other questions. So what are our topics for today? So our concepts for today are relative motion, relative velocities, what it looks like when someone's moving in a reference frame that's moving relative to you, such as what does it look like when someone's moving on a train and the train is moving relative to you, and how do you figure out that? And then circular motion. Okay, well, as I said at the beginning, we're going to have a look at uniform circular motion. Okay, so here are some of the comments from the pre-lecture that you guys made. These are sort of, again, these are typical comments. I'm having some difficulty understanding questions where it asks to find the velocity from different perspectives. Yes, this relative velocity can sometimes be confusing, so we're going to go through it in quite a bit of detail. I've never really looked at reference frames in terms of when the observer is not standing still. Okay, so we're going to do an example like that, so you can see how do you figure it out if like both, like for example, you're moving and there's a moving train, and you want to compare the motion between the two and say, for like someone's in a car driving by a moving train, what does it look like when someone on the train is moving, for example. And then someone else said we'd like some more examples about angular velocity and centripetal acceleration. So I'm hoping to get to one of those by the end of the class. And if we run out of time, then next time is a demos and problems day. And so we'll have more time to go into detail and do some example problems on the various topics. Someone made a comment that they said, I feel like I'm taking too little notes for this class. The format is a little, might not lend itself to notes, obviously, but one suggestion I have is to take notes while you watch the pre-lectures. The pre-lectures are meant to be part of your class lecture, right? So you've got the pre-lecture, which is about 30 minutes total or so of like concepts and discussion, and then we do more on the same topics in class. So I would recommend treating it like a lecture and taking notes. I mean, the nice thing about the pre-lecture videos is that you can stop them and start them again. So you can stop it, take some notes, start it again. Okay, so let's talk about relative motion starting in one dimension. We'll start with one dimension and then we'll go to 2 dimensions. Okay, so this is a sort of a typical relative motion scenario. So we've got 2 different what we call reference frames here. We have the ground reference frame, which you essentially depict as a coordinate system that's at rest relative to the ground. And you can measure things in that coordinate system. For example, here we've got the location of the train in the ground reference frame, so our train ground, and then we've also got the location of Mike, who's a person walking on the train, and we've got his location in the ground reference frame. And then you can also imagine that there's a train reference frame, a coordinate system that's at rest relative to our moving train, and you can also locate Mike in the train reference frame, right? So there's a position vector R Mike train. And you can see just looking at those 3 position vectors that we drew that the position of Mike in the ground frame is equal to the position of Mike in the train frame plus the position of the train in the ground frame. Okay, you can see that those 2 vectors, R Mike train, R train ground, add up to R Mike ground. Okay, so that's positions. And if you want to figure out what's happening for velocities, well, we learned last week that to get velocity from position, you just need to take a first derivative with time. So if we take a first derivative with time here, we basically see that we get the same relationship for the velocities, that the velocity of Mike relative to the ground, and this is a vector, remember, is just equal to the velocity of Mike relative to the train plus the velocity of the train relative to the ground. And you can see I drew those 2 vectors at the top. The train is moving to the right, and Mike is moving to the left relative to the train. Okay, and so if you draw the vector addition diagram down here and we add V Mike train and V train ground, you can see that the resultant V Mike ground is a smaller green vector pointing to the right. So basically the idea is since Mike is moving more slowly than the train, somebody on the ground will see him moving to the right at a speed smaller than the train speed. And that's because he's moving backwards on the train. And intuitively, if you think about it, that makes sense. Okay, that he would appear to be moving more slowly than the train, but in the forward direction. Okay, so there is a pattern here that you can use to figure out which vectors to add to which vectors to get the velocity you're looking for. You can kind of see the pattern here. If we want V Mike ground, then the first velocity vector has to be V Mike train, so the mic has to come first, okay, so that the first subscript matches, and then the last subscript also has to match. So if we want V mic ground, then the last subscript has to be ground, and the second term there, and then the two middle subscripts have to be the same. Okay, so that's the pattern, and if you use that pattern, every time you set up one of these vector sums, it will always work. Okay, so it's always going to be, if you want to know V mic ground, example in this case, it's V mic to train plus V train to ground. Okay, that will always work for your relative velocity pattern, so your relative velocity vector addition. Okay, so given that, I thought we would try one of these. So here is a poll question. So I'm going to set up the poll while you guys have a look at this. We've got 4 choices. This one is a little tricky. If you have questions about the homework, I will answer them at the end. I'm not going to answer them in the middle of class. Okay, there is our poll. Okay, so let's actually read through this one now. So you are on train 1, traveling north, which is upwards on our screen here, at a speed of 100 kilometers per hour with respect to the ground. Your friend is sitting on train 2, which is traveling south at 100 kilometers per hour relative to the ground. Okay, so those are both relative to the ground. As you walk toward the back of your train at 6 kilometers per hour, what is your velocity with respect to your friend? So what we're looking for is what is VU relative to train 2. That's the quantity we're after, okay? And we're looking for the so we're basically looking for the magnitude of that velocity vector. Okay, I think we're going to do about, let's do 10 more seconds here. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. All right, so what do we got? So it looks like the majority think the answer is C, that the speed of u relative to the train would be 194 kilometers per hour. Okay, but we have a reasonable group that think that it might be D, 94 kilometers per hour. So let's give this a try, and I'll show you how I would work it out. Okay, going through it methodically like this. Okay, so how would you figure it out? So I'm going to start with a relative velocity vector addition here to figure out what is the velocity of u relative to train 2. Okay, so u relative to train 2 has to be equal to the velocity of u relative to train 1 plus the velocity of train 1 relative to train 2. Okay, that's our pattern, right? Where we've got the same first and last subscript and matching middle subscripts, train 1 here. Okay, so now we know u relative to train 1, right? They gave us that. That's 6 kilometers per hour. And that would be in the southerly direction, right? Backwards relative to train 1. Okay, so we know that one. Okay, what we don't know right now is what's the velocity of train 1 relative to train 2. Now, can anyone guess or tell me in the chat what's the velocity of train 1 relative to train 2? This is sort of like the scenario where you're on a highway and two cars are passing each other. Right, it would be 200 kilometers per hour, right? Okay, if they're going in opposite directions at 100 kilometers per hour, okay, then the relative speed here would be 200 kilometers per hour. And since train 1 is going north, and we call that, we call that the positive direction, then it would be positive 200 kilometers per hour. If you're not sure how to figure that out, you can do the math to figure it out. One way to figure it out is that you say, okay, I know that the velocity of train 1 relative to train 2, you can show that that's equal to the velocity of train 1 relative to the ground minus the velocity of train 2 relative to the ground. Okay, you can get that from writing out what's the velocity, say, of train 1 relative to the ground and doing your relative velocity calculation. And so if you calculate it that way, and we say train 1 relative to the ground is plus 100 kilometers per hour, and the velocity of train 2 relative to the ground is minus, because it's in the opposite direction, it's in the southerly direction, and we subtract those two vectors, you get that the velocity of train 1 relative to train 2 is plus 200 kilometers per hour. So in the northerly direction. So if you're on train 2, it looks like train 1 is going really fast in the northerly direction as it goes by you. Okay, so now we can take that answer plus the fact that u relative to train 1 is in the negative direction. Okay, you're going backwards relative to train 1, so you take u relative to train 1, which is minus 6 kilometers per hour, plus v train 1, train 2, which is at plus 200 kilometers per hour, and you end up that the velocity of u relative to train 2 is positive 194 kilometers per hour. So well done for everybody who got that one right. So that's how we know it's 194 kilometers per hour. And it would be in the positive direction. So northward in this case. Okay, if you were at rest on train 1, you would be going 200 kilometers per hour relative to train 2, but because you're going backwards by 6 kilometers per hour, it's slightly less. So a bit like the previous example. Okay, so instead of 200, it would be 194. And so if you think about that, that sort of seems to make sense intuitively as well. So questions on that one?
Hello, I had a question.
Sure, go ahead.
According to me, I think that if the north train is traveling 100 kilometer per hour and then the south is traveling 100 kilometer, they are opposite, so they would be canceling each other. So, according to me, I thought it would be 0 kilometers per hour, but then again, like I'm so confused about it.
Right, yeah, so that they wouldn't cancel each other out. You have to think about like I was saying, if you're on a highway and you're driving, or it's better if you're, maybe say you're on a 2-lane road and cars are going opposite directions, right?
Yeah,
Um, so the relative velocity is always the sum of those two velocities when you're going in opposite directions.
yeah.
Okay, they would only cancel if you were going in the same direction. So like if you had two cars on a highway side by side going the same direction with the same velocity, then the relative velocity would be 0. And it's because
Okay,
they're in opposite directions that you have to add them.
okay, okay. Thank you.
You're welcome. So we're going to try this now, so you'll get a little bit more practice. We're going to try this now in 2 dimensions. So here's another poll question. Two dimensions is sometimes a little harder to visualize. One dimension is nice because, like I said, you can kind of imagine it from driving or being on a train or a bus. All right, so let's start this poll. Okay, so consider a boat crossing a river with a downstream current. Okay, so now we're going to have a current, which is a velocity of water relative to the shore. We're going to have a boat, which has a velocity relative to the water, and it also has a velocity relative to the shore, right? Which will be a combination of its velocity relative to the water plus the water relative to the shore. So it says, now suppose the boat needs to get to point X on the far shore. What must be the direction of the boat's velocity relative to the water if it wants to go straight across and get to that point X?
Sorry, so that
This
means
one you
the
might,
velocity of the current is more than the boat?
not necessarily, no. Just which way does the boat need to point? Okay, so which way does the boat need to point relative to the water if it wants to go straight across? So it's helpful to draw the vector diagram, okay? Think about what the velocity of the boat relative to the shore has to look like. We know what the velocity of the water relative to the shore looks like. That's the current. And then you use those two to help you figure out what is the velocity of the boat relative to the water. Okay, let's do like 10 more seconds on this one. All right, 5, 4, 3, 2, 1. Let's see what everybody thinks. Okay, so what do we got? We have the vast majority are going for C, that the direction of the boat's velocity relative to the water must be diagonally upstream, so diagonally opposite the direction of the flow of the water. That's what that would mean. Okay, so let's see how you would figure this out. Okay, so again, the flow, the current, you would call that the velocity of the water relative to the shore, so VWS. Okay, we want the boat shore to be vertical here. We want the boat to be able to go straight across and get to a point on the shore on the other side that's directly across, okay? And we know that V boat shore is a sum of V boat water plus V water shore. And so that's going to tell us which way V boat water has to point. Okay, basically, if you put in the water shore vector up at the top there, next to the boat shore vector, you can see that the vector that you need to add to VWS, V water shore, to get V boat shore has to point diagonally upstream, that the velocity of the boat relative to the water. In other words, you have to go partially upstream to counteract that flow downstream so that you go straight across. So this is one you could sort of figure out intuitively if you think about it, and if you've ever been on a boat, right, or get some feel for the idea that if you want to counteract that velocity that would push you downstream, you have to go somewhat upstream. So the answer is, in fact, C. Okay. So this is a case where your intuition might be helpful, okay, in this regard. In other cases, sometimes it's less obvious. Now, this one does relate to one of the questions in the pre-lecture, okay? And that's because one thing to notice here, and this is related to the question someone just asked, which is the size of these velocities. So you can see this only works, you can only possibly get straight across if the size of the velocity of the boat relative to the water is bigger than the current velocity. Because you can see VB water there, VBW is the hypotenuse of that right triangle. So it has to be bigger than the current. If VBW is not bigger than the current, you can't go straight across. And that was the example in one of the questions contained within the pre-lecture, where they said, now we've got someone who swims, and she can swim at 0.4 meters per second, but the water in the stream is moving at 0.5 meters per second. So she is swimming more slowly than the current. And in that case, it's not possible for her to go straight across. Okay, you can cross the stream if your swimming speed relative to the water is less than the water, but you will never be able to go straight across. And you can see that vector sum down below, where you can see that if Vs, if its magnitude is less than Vw, okay, then again, because Vs is the hypotenuse of that, would be the hypotenuse of the triangle if you went straight across, it's not big enough, right? And so you end up with essentially the water pushing her downstream. So the swimmer relative to the ground or the shore, she can't possibly go straight across. The water pushes her further downstream, and she ends up to the right of that X. Okay? They are being head to tail. Okay, so here it's the sum of the swimmer relative to the water plus the water relative to the shore or the ground is swimmer relative to the ground. Okay. Okay, so I'm not sure why your visualization, I don't know if this is about this one or the previous one. Okay. But this is showing the previous one. If we go back to the previous one here, okay, again, right, we have a vector sum. Okay, so we take vector BW and we add vector WS and we get vector BS. Okay, so we are, we draw WS at the end of vector BW, and then the resultant starts at the beginning of BW and ends at the end of WS. Okay, good. I'm glad that helped. Okay, maybe it's some of this I think is just remembering how to do vector addition. Okay, and getting more familiar with that again. Okay, so we're going to actually do an example now where I'm actually going to work through it for you. Okay. So you are traveling on an airplane. The velocity of the wind, the air with respect to the ground. So now we're going to have wind instead of a current, but it works very similar to a current in a river. And we have the velocity of the wind is 50 meters per second at an angle of 45 degrees east of south. Okay. The plane flies at a speed of 200 meters per second due west relative to the ground. Okay, so that's it's so say it's traveling between 2 points on the ground, right? And it's trying to get someplace due west of the other place. Okay, and then the question is, what must be the velocity of the plane with respect to the air? Okay, so this is what it's going to look like. All right, so whenever you do one of these problems, the first thing you want to do is draw a picture. All right, and then work from there. Anytime you're doing vector addition of any kind, whether it's velocities or when we start adding forces, I really think you need to draw a diagram so you can see what your vectors look like, so you can understand how you might add them together. Okay, so this is where we're starting. Okay, there's our velocity of the air relative to the ground, 45 degrees east of south. Okay, or you could also call this 45 degrees south of east since it's symmetric there. And then there's our airplane relative to the ground going due west. All right, and we know, again, okay, that V airplane ground is got to be equal to the velocity of the airplane relative to the air plus the air relative to the ground. Okay, so in the one we're after here is V airplane air, right? What must be the velocity of the plane with respect to the air? Okay, so what I'm going to do now is I have my document camera. So I'm going to switch to my document camera here. And we'll work this one out. We'll wait for it to come up for you guys. There it is. Great. Okay. So I'm going to turn it a little bit sideways to make it a little bit easier for me to write on this. And let me know if I go off the screen. Sometimes I don't notice and I go off the screen. So I'm going to write this like this. So I'm going to call it plane instead of air, just so that we have a third subscript. So it's plane to ground equals velocity plane to air plus velocity air to ground. Okay, and we know that the magnitude of plane ground, right, is 200 meters per second. So I'm writing everything down, writing down everything I know. It's always a good way to start. So write down everything you know, and the magnitude of air to ground is 50 meters per second. I'm not going to redraw the diagram we have. We have the diagram on the slide, which we'll go back to. So, like I said, we're after this one. What's the velocity of the plane relative to the air? So to get that, I'm going to subtract VAG from both sides here. So I'm going to write a vector subtraction that V plane air must be equal to V plane ground minus V air ground. So there's my vector subtraction. Okay. All right. So now I'm going to draw this out. Okay. I know that V plane ground looks like this, points to the left, to the west. Okay. And now I want to subtract VA ground, which is the same as adding minus VA ground. Okay. So it's going to look something like this. All right. So this is V plane ground. This is minus V air ground, where this is 45 degrees. Okay, and if I add those two vectors together, I get a vector, and I'm going to do my best to freehand this, that looks something like that. Okay, not super straight, but that's the idea. So this is the velocity of the plane relative to the air. Okay, so where, just to draw in our coordinate system, this was north and this was west. Okay, so I just need to add these two vectors together to get this vector. So the first thing I'm going to do is break this one up into components, because mathematically that's the easiest way. Okay, and so this one is going to be VAG cosine of 45. And this is VAG sine of 45. Now, as you know, those are both the same size, right? Because 45 degrees is the mid angle there. Okay, and then I'm going to look at my separate components. So if I start with my west component, VPA west here is just VPG plus VAG cos 45. So the magnitude of VPG plus VAG cosine of 45, which looks something like this. VPG is 200 meters per second. VAG is 50 meters per second times the cosine of 45. And I get that my westerly component, the length this way, is about 235.4. It's bigger than 200, which is what we expect. Okay, so that's my westerly component of the plane's velocity relative to the air. And then I can do my north component. The north component is a bit easier because it's just this component. Okay, so VPA north. I'm using north and west because they gave me north and west. Okay, if they don't give you north, south, east, west, then it's better to use X, Y, Z typically. Okay, so this is going to be VAG sine of 45 degrees, which is our 50 meters per second times the sine of 45 degrees, right? Which is equal to 35.4 meters per second. So we have 35.4 in the north direction, 235.4 in the west direction. And now to get the magnitude here, right, we just do Pythagoras. Okay, so we're going to have VPA, the magnitude, is just the square root of 235.4 squared plus 35.4 squared. That's our Pythagoras. And what do we get? About 238 meters per second. So that's the magnitude of the velocity of the plane relative to the air. So we're half the way there. Okay. And then the other thing we need to figure out is this angle here, which I'm going to call theta. And now we can get that angle using the tangent. So I'm going to need a little bit more space here. And so now the tangent of theta is just 35.4 over 235.4, right? The north component divided by the west component, and that gives me a theta of about 8.55 degrees. Okay, small angle seems to make sense because west component is much, much bigger, right, than that north component. I didn't quite draw it to scale, right? Okay, and then to label it, you can't just write an angle, you need to say where the angle is, and you can see that this is north of west. So I'd write this as north of west. You do want to specify either which way the angle is pointing like that, or draw a picture one way or the other to give a complete answer here. Okay, so any questions on that? I will post that so that you guys can see it. Okay, so in this case, yeah, you'd want to use degrees, but there are other cases where you're going to want to use radians. So in this class, you will be going back and forth between degrees and radians, depending on the type of problem we're doing. So you'll have to be careful and aware of which mode your calculator is in. You can use any kind of calculator that does not have Wi-Fi attached to it. Okay, so we're going to stop that now. Okay, unless there are any questions. And we're going to go back to our PowerPoint. Where were we here? Okay. All right, so you could call them negative if you wanted to have an XY coordinate system. okay? But I was just using a north component and a west component, okay? So you don't have to make them negative, okay? If you're talking about a north component and a west component, okay? You can do it either way. If you want, if we're talking about x, y, and you define positive x to be east and positive y to be north, okay, then you would want to set all your westerly things to be negative, but the north would still be positive. Okay, so we've got like 10 more minutes, so I did want to talk a little bit about uniform circular motion for the rest of the class. Whatever we don't get to today, we can do a little bit more on Wednesday. So uniform circular motion is an interesting case of two-dimensional motion because it's a situation where the speed, the magnitude of the velocity is constant for an object moving in uniform circular motion. Okay, but the direction of the velocity is changing. And as we know, if a velocity is changing, that means that the object is accelerating. Because we know that the definition of acceleration, of instantaneous acceleration, is the time rate of change of velocity, dv dt. Okay, so, and we can actually figure out how big this acceleration will be for an object moving at a constant speed along a circular path, okay, by looking at our two velocity vectors there, our velocity at time t and our velocity at a time ever so slightly later, okay, at time t plus dt. Remember, dt represents a tiny little amount of time, a very small delta t, okay, and you can see in that small amount of time, the velocity vector has basically changed its direction, okay, by an amount d theta, but has not changed its magnitude, okay? And you can determine that the change, okay, dv in the velocity here is just equal to that constant speed v times the amount of angular change d theta. And they went through all of that in the pre-lecture, and that tells you then, if you take v d theta and plug it into our acceleration definition, you get that for an object in uniform circular motion, that the magnitude of the acceleration is equal to the speed v times how fast the angle is changing, d theta dt. Okay, and so the faster the angle is changing, okay, the larger your acceleration will be. So for example, if you're turning a car, if you're turning it in a tighter circle, okay, then that'll represent you changing the angle faster, and that will require a larger acceleration, which, as we'll see, requires, for example, more friction on the road to keep you on the road. Okay, so that's sort of the basic idea of the fact that uniform circular motion means that the object is accelerating because the velocity's direction is changing. And in fact, you can also show, as you can see here, that that acceleration vector must point towards the center of the circle. You can see that that red vector A points in the same direction as the dv, which it should, which it has to. Okay, so let's have a little bit of a look at this quantity d theta dt, which is how fast the angle, okay, is changing with time, okay? So we usually call this quantity omega. So little omega, that funky looking w, is the rate at which the angle theta changes. It's defined to be the theta dt. We usually call it the angular velocity, or sometimes we call it the rotational velocity. And we typically measure it in radians per second. So here's an example where we're now using radians instead of degrees. And there's a good reason for that, and you'll see why in a second here. Okay, if you go now and look at an object moving in a circle, and you, for example, watch it move an angle theta. So watch it move such that it traces out on the circumference of the circle a distance s, which we'll call the arc length. Okay, and hopefully you remember from your math class that if you measure theta in radians, that arc length s, that distance that our object has moved, okay, is equal to the radius of the circle times the angle theta in radians. Okay, so that's how far the object has moved in linear distance. And so if that's true, then the speed, right, is just ds dt, right? It's just the change in position with time. We can plug in our theta for s and then realize that for something moving in a circle, r doesn't change. And so we get v is equal to r d theta dt. Or the other way to write it is that the speed of the object is equal to the radius times the angular velocity. Okay, and that's going to be a quantity that's going to come up again for us later when we look at rotational motion. Okay. And you might say, does that make sense? So things to notice here, first of all, that omega is in radians per second. And then when you multiply it by r, you're going to get a speed in meters per second. And you might say, well, where does that radians go? Well, radians is a weird kind of unit that doesn't have dimensions. And so radians is a unit that's going to kind of come and go depending on where you need it. Okay, so in this case, when you do r in meters times omega in radians per second, and you get an answer in meters per second, what you've done is basically crossed out the radian, okay, and said that we know that velocity is in meters per second. So, but there are going to be other times, for example, where you're given a velocity in meters per second and you have r in meters and you're trying to figure out an omega, and you're going to have to plug the radians in again. So you'll see how that goes when we do some example problems here. So now if you think about what would happen if your path were one circumference, if you went once around, okay, then we know then that, again, the speed would be the total path length, which is the circumference, 2 pi r, divided by the time it takes to go around once. And we call that capital T, otherwise known as the period of the motion. So the period is always the time it takes to go around once in a circle when you're talking about uniform circular motion. It's also, we'll see the time for a complete oscillation when we start looking at oscillating systems. Okay, and then you can see if you divide both sides by r, you get that your angular velocity is 2 pi over the period. And if you think about it, that makes sense because 2 pi is the total angle that you move through. 2 pi radians is the total angle you move through when you go around once. And again, t is the time it takes to go around once. Okay, so it seems to make a lot of sense here. And then if we put it all together, before we do that though, just to point one thing out, there is one issue with circular motion here, which is that it does matter which way around you go. Okay, so we have a convention to sort this out for now. We typically say that our omega is positive if you're going counterclockwise. Okay, so if you start at the horizontal and move counterclockwise, that's usually considered to be the direction of increasing theta. And so omega is positive, and then omega is defined to be negative if you're going clockwise, if you're going the other way around. Later on, when we do rotational motion, we will define omega as a vector quantity, which will also help us determine which way around you're spinning or moving in a circle. Okay, but for now, we will just use this convention of positive and negative for counterclockwise and clockwise. And most of the time in these problems, we won't even actually care about the direction. We'll just be talking about magnitudes of these things. Okay, so if we put this all together, so we saw that the angular velocity was v over r, okay, and that this acceleration of an object moving in a circle is v times omega. And if we put it all together, we get that this acceleration for an object moving in a circle with uniform circular motion is equal to v squared over r, or omega squared times r. Either one of those expressions is correct. And we give it a name. We call it the centripetal acceleration because it points towards the center of the circle or the circular path. Sometimes we'll be looking at things moving in complete circles. Other times we'll be looking at something that moves part of a circle. Okay, and so you'll have to imagine where the rest of the circular path is. So I think that we're going to stop there because we've run out of time. So next time we will get a little bit more into centripetal acceleration, and I will do an example problem, and then we'll do some other example problems for two-dimensional motion. So we will stop there, and I will stop recording.